Okay, thank you for the nice introduction. So my name is Heinz Riener. I'm a postdoctoral researcher in EPFL. I'm going to talk about the EPFL logic synthesis libraries. I'm actually just back from the US, so for me it's now really, really early. So it's around my inner clock is around 5 in the morning. So if I sound a bit tired, that's really the case as well. Okay. Yes. So I'm going to talk about the EPFL logic synthesis libraries, and I want to tell you in the beginning, if you like this project, then please star and fork us on GitHub. You can follow this link, and then you can see an overview of what I'm going to talk about today. Okay, and this project is not so when I talk about here source code, which is implemented, I didn't implement all the source code. There's a lot of people in our lab, they contributed to this project. Also, there are a lot of people from the open source community who contributed. They provided us with code, with pull requests, and so on. So thank you to all these people for their great work. Okay. And this project is a research project. It's called EPFL Logic Synthesis Libraries, and we are actually in EPFL we are the Integrated Systems Group. So we do logic synthesis algorithms. And if you don't know what logic synthesis is, then I try to explain you that in a few words. So if you do RTL, then at some point you want to end up with something for your ASIC or FPGA. You want to have something which you can program there. And then you have some compiler which translates from RTL into an ASIC or into an FPGA. And this compilation step is really complicated, and there are many, many different steps involved. And one of these steps deals with optimizing combinational logic at a technology-independent level. So technology mapping comes later. And this exactly is done with logic synthesis. And we do research in this area, and we develop infrastructure for logic synthesis. And in this project, we develop infrastructure for logic synthesis. We started around 2 years ago to implement everything in open source, to build up modular libraries, which focus on different core aspects of the problem, which you can put together and then solve more complex research tasks. We try that everything is well tested, that everything is well documented and also easy to integrate. Currently, there are 8 libraries. They all have these nice logos, and they have some name which hints on what they actually do. Half of them focus on conventional logic synthesis tasks, if you want to, and half of them focus on quantum combination. Quantum combination is the process of getting from a quantum algorithm into really something which you can run on the quantum computer. So this is really programming the quantum computer. And this process of translating from a quantum algorithm into some program for the real quantum computer, this is quite similar to what we do in logic synthesis. So this is kind of the translation step, and you can optimize in between, and you can do really, really well and use kind of the same techniques. These two, now I showed you this separation of these two libraries. This separation was just to explain. So the quantum compilation framework also uses truth tables. It also could use the command shell library and so on and so on. So they are really could be modularly put together. So we have one white paper on this whole idea on arXiv. You can check this out if you're interested to read it. It focuses on only 4 libraries, so it's a bit older. It's 1 year old, and we plan actually to update it with all the libraries soon. Okay, here's a link to where you get more information about this project. Okay, the motivation for this project is, as I said already, we try to build core libraries for dedicated synthesis tasks, well documented, well tested, easy to integrate. We try to provide state-of-the-art algorithm. We want to provide people with the common functionality which is shared over large projects, such that you don't have to reinvent the wheel all the time. So actually, the focus here is a bit more on research people. So our PhD students, every year they have to kind of, if they start in our lab, they have to do the same steps and same tasks, and kind of they have to read in the same benchmark formats and so on, and these libraries can get them started way faster. Okay, we try to make everything open source to allow everything to use them and to contribute. We have a vivid collaboration with UC Berkeley. These are with Ellen Mischenko, who builds ABC, and we integrated a lot of his knowledge, actually lessons learned when we started to implement these libraries. And we see this project as a research enabler, so it should help actually other people to get started. Here on the bottom, I put a couple of logos from other institutions, universities, people who use actually these libraries. I don't really know the exact details about this project. It's mostly because people send me an email and say, okay, I tried this or that, how do I integrate this? And then I know, okay, there's someone who uses libraries, and there could be way more people. It's interesting, so we have one project actually where, so we built quite generic libraries, and we have one project where someone tries to integrate this with C3, with the Microsoft Constraint Solver, and he can apply actually our logic synthesis, our logic optimization algorithms basically to optimize Boolean constraints in the Z3 solver. And the other interesting project is I think this one is quite recent. So there are people from Rigetti, this is a startup company, they built their own quantum computer, and they started to use our libraries, and they say actually they do better than before, which is quite cool. Okay, we presented this work in a couple of actually mostly conferences or mostly workshops associated to conferences on open source. Also, we were in FOSDEM this year. We were at the part of the FEDER meeting in Open Source Academia EDA Software last week in DEC. Now we are here. Next week we will be in the Logic Synthesis Software School in Lausanne, which brings me to the next point. Next week there's the Logic Synthesis Software School in Lausanne. If you're interested in logic synthesis, then come to us. We have interesting speakers. The event is actually free. It's a satellite event of the International Logic Synthesis Workshop, which is this year in Lausanne. Normally it's in the US. And so the workshop is from 21st to 22nd, and this event is kind of the day before. For the workshop, you have to register. Actually, you can find out all the details here, and the LSS event is for free, and you could just come. But you have to send us an email that we have enough seats at some point. Okay, this project is funded by EPFL themselves, by the EPFL Open Science Fund, which funds kind of so they support unfettered dissemination of scientific discourse. This is actually open science, so not only open source, but open access, open benchmarks, reproducible results. We want reusable results, and we try to achieve all these goals. Okay, let's talk about the libraries now, finally. So everything here, what I tell you is implemented in C++. We try to do it in modern C++, so this is software. We try to use C++ 14, some parts are actually C++ 17, so if you want to try this out, you need a very recent compiler. We try to have, we don't want to have complicated build frameworks or anything else. We try to build everything header only. So the only thing that you have to do is you go to the website, clone the repository, add the directory to your include path, and then you include the right file, and then you're ready to go and use our libraries. Nothing complicated to build. We try to have almost no dependencies. So if there are dependencies, then we look for header-only code, and we try to ship them with the libraries, such that you don't have to download extra other projects or build them first. Of course, we try to do modern software development, so everything is under version control. We have everything on GitHub. We do continuous integration with Travis and with AppVeo for Windows. We have read the docs documentation, also there's a bit of Doxygen. We try to have coverage analysis, with coverOrs. There are some parts which are built automatically, the Python bindings, which can then be integrated, for example, in Jupyter Notebook. This is pretty nice because all the quantum people actually love that. Okay. Okay, here's a small example. So we built this example for our paper actually, just to give people an idea of what you could do just with a few lines of code by putting your code together. You can check this code out, it's online as well. So the idea is, you can see here a simple program which has a command line shell interface. It can load truth tables. It can load truth tables actually from a bench file. This is kind of some format which we standard. So we have some benchmarks which are standardly available in this format, and then you can compute optimum networks for these truth tables. So given a function, we want to have the optimal network, so something like with minimal number of nodes. Okay, and now I walk you again through this demo. So you can run this demo. Then there's a help command. It shows you all these commands. So it's a standard shell interface like Yosis has it or like ABC. Then you can ask for help from the load command. You can load some hexadecimal functions. So cafe this is hexadecimal. You can show which function you actually loaded. You can do NPN canonization. I don't go into the details here. If you don't know what it is, you can look it up in a paper. And you can load all these functions from a file. So our 3 variable functions from this file, you see all these functions which are inside. Then you can select one of these entries from the store. You can search for an optimal network. It computes an optimal network, which is here called Boolean chain, because it's this is a notation which comes from Donald Knuth, actually, from the art of computer programming. Now, the computer these optimal chains, and then there's some form, then you can print it, and this is kind of the circuit. If you know how to read it, then you would see that this is a circuit. Okay. And the nice thing is you just can do that in 268 lines of code, and if you go really on the site and see, then this actually includes commands and new lines and all kind of other things. So it's way less even. Okay, and I wanna now use the rest of the time just to walk you a bit through the source code, just to have an idea how this works. Okay, let's look at Alice. Alice is a command shell interface, command shell library, C++ code. We have a bit of macro syntax here to make it a bit nicer. And you say you want a main function, you want a store, and in the store should be optimal networks. Then there's some stuff to just tell the compiler how these store elements are named and so on. Okay, and in the store we want to store a truth table, and we want to store the string of this network when we found it. Okay, so Alice is a command shell library. It has some general shell features. You have something like command completion, you have command history, you have automatic logging for JSON. This is really nice when you want, for example, to store your results in some file. You don't have to, I don't know, if you're a PhD student, then you often write some algorithms, then in the end you print out your results, and then you have to fill in some table in the paper, and then you do very messy grep and awk in order to get this data out. And this is really nice. You get a JSON file, and you write one Python script which just gives you the right entries, and you can nicely present it. No more awk and grep. Okay. We support multiple store types. We support multiple store elements. Basically, you can interface this with other stuff, like with ABC. You can store a GR main graph. You just provide it here, or word level networks. You can provide this in one file. Then you can something like build your own ABC clone with a nicer interface. Okay, we have an automatic, so we have easy bindings for Python and C in that case. You don't really need to modify your code. You can just enable this by compile time. Python interface is nice because you have Jupyter Notebook integration, similar for C things, and then it's pretty nice that you can interface with other languages like .NET, JVM, and Tcl, and so on. Okay. Of course, you can show store details by using these macros. There are other macros for implementing, for example, print status, show read and write. Okay, I do a bit faster because I'm running out of time eventually. Okay, then you can implement custom commands. Something like if you want to, so now we don't use the macros anymore. We want to have our own load command. So we derive from the command class. Provide some text what we want in the helper, in the help output. We add some options, some flags, and whenever we execute this command or type this command in the shell interface, then this code is actually executed. There's something like validation rules, so you can check the parameters and flag some errors to the user. You can specify what is locked in the JSON file. Finally, we store the truth table here, and we have to register this command. Okay, this is basically what Alice provides you. Pretty easy and very easy to use. Okay, then there's another library which is called Kitty. This is a C++ truth table library. It provides you with two data structures. One is a static truth table, the other one is a dynamic truth table. The difference is, in one case, you have to know the number of variables at compile time, and the other case, you have to know the number of variables at runtime. The feature of this one is it's always stored on the stack, and this is typically faster than the dynamic version. The disadvantage is you have to know the size at compile time. Okay, how you use this? Static truth table, you provide at compile time this number of three, so you know 3 inputs has this truth table. Dynamic truth table is the same. You can provide the size, but dynamically as a parameter. Otherwise, you can use it completely the same, XOR of this 3 ABC, ternary majority of ABC. Exactly the same for both. Don't have the time to go into all the details, but there's really an extensive documentation. You can read everything up. Changelog, the algorithms which are supported, the internal data structures. Okay, we have some interesting algorithms. So you can do NPN canonization. You can create, for example, functions directly from Boolean chains. Something like if you have this straight line program, this comes out of a research paper which gives you some AAS expert boxes, so in this case is an inversion. Then you can just provide these strings, call, create multiple from chain, and it would give you the Boolean function here as outputs, which implements actually this stuff here. Okay. Then we want to read truth tables from a file. So we implement load bench command. This is another command. And we use here another library which is called Riener. Riener provides parsing for the standard file formats which we have in the logic logic synthesis. I go here still a bit faster. Again, these standard formats are typically, we have something like Eiger parser, bench parser, Bliff parser, PLA parser, something a very, very simple structured Verilog parser because benchmarks are provided in this way. This is a lightweight and customized parsing library. It's flexible, easy to use. It doesn't only do the parsing. It does not do anything with stuff, but it provides you with callbacks, which you have to implement, and then something happens. For example, here on gate, we implement the bench reader, and then it gives you this on gate function. It passes the information, and whenever it sees a gate, it provides you with this information, and you can decide what to do. There's one crazy thing about these ORD file formats. They are not topologically sorted. This is really annoying when you read in ORD benchmarks. We automatically sort topologically, and we provide you these callbacks in the right order. There's a bit of diagnostics which you can do. There's an optimal network library which is called percy, which does exact synthesis. So this synthesizes you from a function an exact minimal network. This is done with SAT solving in the backend. So you provide a specification, a function, you choose an encoder, you choose a solver, a SAT solver, and then you get the optimal network out of that. Okay, we have support for different SAT solvers. You can do this in parallel. There's a bit of deck topology concern. This makes it a bit faster, so there's a bit of optimization tricks here. And it's flexible because you can compose here a lot of different encodings together. There's example code which shows you how this works. And then there's the last library, which is mockturtle. This is the logic network library. Here you have a couple of different network types. So you can specify a network, then you can read a file in this network. You can apply a logic optimization algorithm, something like cut rewriting, do LUT mapping on this AIG, and so on. The nice thing is these algorithms are generic. That does not work only for AIGs, but for MIGs. Go here, still a bit faster. Sorry, too fast. Okay, I missed it, but this does not work only for AIGs, but for MIGs, XMGs, XAIGs, and all kind of standard data structures that people provided. The idea here is that the algorithms are implemented with an abstract network API, which gives you some which is a collection of names on which we agree. Then we implement the algorithms on top of this abstract network interface API, and later on implement the network types. And then at compile time, when you have your algorithm, which is implemented with your abstract interface API and provide your network types, which actually provide implementations of these agreed names, you would see all names are actually implemented, which are necessary for this algorithm. And then this instantiation would work, or you get a compile time error if you forgot to implement something. On top of that, you could still put some performance tweaks which actually use the network implementation, which actually use some information which is only available from the network, from the specific network implementation. Okay, then there are some other highlights, tweaks. We have a couple of optimization algorithms which you can use. There's an extensive documentation. So to sum up, we extracted some well understood and often used algorithms into modular dedicated libraries, which can be used and plugged together. We have documentation, testing, micro-benchmarking, continuous integration, version control. We did it right from the beginning, which is pretty nice. We try to avoid dependencies, except for other small and lightweight libraries. And we love to share that with other people. If you like this project, please star and focus on GitHub. Thank you.
Thank you very much. Questions?
I'm sure you know about WOSH. Clifford Wolf's here for the conference. I just wonder whether it would have been better to use his software as a front end rather than write your own Verilog parser.
Sorry?
If you use WOSH, that uses ABC as
Yes.
a back end for synthesis.
Yes.
Perhaps your product could be more easily showcased as an updated back end for WOSH, then you wouldn't have to write your own Verilog parser and everything.
Yeah, that's correct. Also, we don't really we don't really implement a Verilog parser. So we only implement a very simple, very simple structured Verilog subset in which typically logic synthesis benchmarks are provided. So these are just sequences of lines of assigned statements in which combinational logic is specified. This is actually implemented, and this is implemented because there are common benchmarks which people use in logic synthesis competitions and so on, and we can read exactly those benchmarks. And of course, one interesting goal could be we could integrate it into some bigger flow tool, something like WOSH.
Questions? If not, let's thank the speaker again.